Okay. Shh. We have about 45 minutes. So today I want to talk about now cooling curve. Okay. So in the last two classes, we will keep talking about Gibbs energy and the phase-time relationship. Okay. So that's what we have actually talked about. And also one of the actually important thing we have to understand from phase diagram is, okay, at given temperature and given composition, what kind of phase is forming. That's basic about the phase diagram. And also the phase diagram is very frequently used in the solidification. Okay, to understand how does the microstructure will be changed with the time and the temperature. Okay, during the cooling or during heating. Okay, that's actually basically what we actually learn from, what we can learn from phase diagram. Okay, so cooling curve. Okay, so let's look at we have like this. So this is A and this is B. And if this composition is 0.666, this compound should be A, B2. Am I right? And we have liquid phase. Okay? And then I don't know what's actually the first, when you have phase diagram, if I don't give you, if you don't actually have the phase map, phase name in each area, at least you have to know how to actually put the phase name. And so, for example, at this point here, in entire this range, left side you have A, right side you have AB2. So this is A plus AB2. Both of them is of course solid phase. Okay, here A plus liquid, L, liquid. And same thing, liquid plus AB, AB2, sorry. And this one, AB2 plus liquid. And here, liquid plus B. Is it okay? So we have phase like this. And now, let's take this composition, for example, 0.9. And then let's take this one, 0.1, sorry. Let's 0.4. Okay? So, I will actually cool the temperature at 1, or composition at 1. And from this temperature to the very low temperature. And then I want to know what kind of phase is forming according to the equilibrium phase diagram with the cooling of this actually this composition. So then what I'm expecting is like this. This is cooling time. So we are assuming that delta H, the heat extraction, is constant. So for example, I am taking 1000 joule per minute. So we are taking same amount of heat continuously from the system. Then the temperature of the system will actually go down. And then I don't know what kind of phase is forming during those kinds of actual cooling process. Okay? According to the equilibrium phase diagram. Okay? So let's take at 0.1. Okay. At the highest temperature. So this is temperature basically, and this is cooling time. Cooling time is basically, so with the cooling time the temperature should decrease, yeah? So from here to here at this temperature, so let's take this one. So let's take this one as 1000 degrees Celsius. Let's take this one as 950. And let's take this one as 700 degrees Celsius, for example. Okay? So I'm cooling down from, let's take this one at 1100 degrees Celsius. I have material at this point. Now I'm cooling it down to the 950. So until 950, I'm cooling it down. And this is only liquid state. Yeah. Okay. So if you know the heat capacity of the liquid phase, if you know the enthalpy of solution of liquid phase, you know how fast you can actually cool down the temperature too. Yeah. I mean, we know how much heat we are taking out every minute. So then we can even calculate what's this slope basically. Okay. This slope is kind of the CP. Yeah. Now, if you touch this one, now you start to have solid plus liquid phase. Yeah. So typically the heat capacity for the solid and liquid is different. Yeah. So temperature profile with of the enthalpy is different between solid and liquid phase. So there's always change of the slope when you actually change the phase, actually the region. So steeper or it can be more flatter. It's depending on the case by case. Okay. So I don't know exactly how the J doing, but let's take a little bit more flatter. Okay. Until 700 degrees Celsius. Okay? And then there's very interesting stuff happen. So at 700 degrees Celsius, it's not actually cooling down continuously like this anymore. It takes actually time to keep the same temperature. And then it's cooling down again. So this area is liquid plus A, and this temperature is liquid, and this is A plus AB2. So it's happening like this. So let's look at this way. So why we have this kind of phenomena? Okay, why we have we call that as a thermal hold. It's actually holding at the same temperature. So that's actually very interesting phenomena in the solidification. Or it's actually happening during the phase transformation. So when you have liquid to the liquid, it's only enthalpy change of liquid phase, okay? So it's continuously decreasing actually its temperature with the taking out the heat. And then here, at this point, your solid is 0 amount, and your solid amount is increasing and increasing and increasing with the decreasing of temperature. So from the Liber rule, so at this point, solid is 0. Liquid is 1%. At this one, this amount of solid, this amount of liquid. Divided by, of course, entire range. And here, this amount of solid, this amount of liquid. So the amount of solid is increasing from 0 to certain value continuously. Okay? So there's no sudden increase or sudden decrease. Yeah? So it's continuously changing. So the slope can be changed, but it doesn't actually stop actually the decreasing of temperature. But at this one, it's very interesting. At this point, just above this eutectic temperature, we know that now this is eutectic reaction, just above the eutectic temperature, we have this amount of liquid, this amount of solid. Just below the eutectic temperature, we have 0 amount of liquid, and then we have this amount of the AB and this amount of A. Okay? So it's a discontinuous change. So it suddenly increased the amount of the certain phase, solid phase, suddenly decreased the amount of liquid to certain value to 0. It's suddenly happening just by changing 1 degree of the temperature. Is it possible? By 1 second? No, it's not possible. By instant. It takes time to change that actual state. So liquid should be from 20% to become 0 or something, yeah? So we have to know, there's the time to actually consume all liquid and transform to the solid, okay? So it takes time. It's like exactly the same thing as water. So if you increase the temperature of water, keep increasing until 100 degrees Celsius, it takes time to boil it completely at 100 degrees Celsius, and then gas temperature is going up again. So exactly the same phenomena, okay? Because there's the complete change of a certain amount of solid or liquid become the other actual phase amount. It's not continuously changing. It's sudden jump of the amount. So it means it takes time to actually complete those kinds of phase transformation at the exactly same temperature. So that's why we need time here. Okay? So here, this is eutectic. So liquid plus A plus AB2. It's all existing together, yeah. So when you have when you have cooling or heating of material, so heating is exactly the other way around, yeah. The other process. It's a reverse process, yeah. So when you cool down some material, or when you heat up some material, whenever you see the invariant reaction point, it's invariant reaction. Invariant reaction, you have thermal halt. So this is always happening. Okay? So by using this kind of the cooling curve, people actually determine the phase diagram in the past. Okay? So they just have the 1 kilogram of the AB mixture at the given composition, put the thermocouple inside, and then cool it down continuously, and then monitoring the temperature change. And then you see this kind of profile. Then, okay, first of all, there's some kind of change of slow. Okay, there's some phases forming. I don't know what phase it is, but there's some phases forming. And there's some kind of thermal halt to certain temperature. There's invariant reaction somewhere here, and then going down. That's how actually people determine the phase diagram in the 1930, 1950. Okay, and this is called thermal analysis. Thermal analysis. So that technique we call it. And exactly the same type of version is still using in the recent years, and that's called the DTA or DSC. So it's same kind of technique. So DTA is differential thermal analysis, and DSC is differential scanning calorimeter. But both of them actually measuring the temperature change of the sample with the cooling or with the heating. Okay, so this is basically one of the technique for thermal analysis. Okay? So, when I ask you, okay, draw the cooling curve of the composition number 1, you have to draw it in this way. Okay? And then, if I ask you, okay, now, during this curve, also please put the kind of schematic schematic microstructure of your material. Then you have to now add this kind of information. So if I say, okay, just tell me what is the microstructure at 1000 degrees Celsius. Then, okay, typically under the microscope, so it's circle. Now in this day we have the square. The picture is taken as a square. But if I give actually circle, you have the period of actually what's the actual phase inside of circle here. So this is 100% liquid here. There's nothing else, liquid. And composition of liquid, okay? So that's actually the microstructure I wanna actually get from you actually the answer. Okay? And here, let's just now 800 degrees Celsius. What is my microstructure? 800 degrees Celsius. So 800 degrees Celsius, let's take it here. So 800 degree. And then let's take this one as 0.3. Okay? So now I have liquid plus A existing together, and the liquid composition is 0.3 moles or mole fraction of XB. And then A is the pure A, yeah? So we have liquid phase, and from the liquid, A is start forming. So A is start forming, like, you know. I mean, the morphology of A could be whatever, dendritic shape, but whatever, you can just assume it's like almost spherical shape, particle like this. And then this is A, and XA equal to 1 in this case, yeah? So XB is 0. And liquid, XA composition is 0.7. Okay? And now, how about phase fraction? You have to even say what's the phase fraction of these two phases, yeah? From the Liebel rule. So from the Libre rule, we say that, okay, so the amount of A phase is this divided by entire length. So it means 0.3 minus 0.1 divided by 0.3. Yeah, so it's 66%. And 30% of liquid phase. In terms of mole, yeah, it's not exactly weight because the unit here is in mole fraction. If this is the weight percent, then it's much easier. We can say that the weight is something. Is it okay? And then, same thing, now at 500 degrees Celsius. So this is 500 degrees Celsius. So 500 degrees Celsius, we know solid plus liquid together. Yeah? Oh no, that's only solid phase, sorry. A plus AB, AB2. Okay? And if you want to really draw this phase diagram very well, then you have to consider this eutectic reaction. Okay? So during the eutectic reaction, so we originally have all solid phase. So the amount of solid phase here is this divided by entire length. So 0 point, so at the eutectic point here, just before eutectic reaction, so we have 0.3 divided by 0.4 of the solid A. So it's 75% of the A solid and 25% of liquid remaining. Am I right? So theoretically, so this is A phase. And because this, and then the rest of them was originally liquid phase before the eutectic. So I'm just talking about at this point. Okay? So before we have A and the liquid at the last minute here. And then during this transformation, liquid become AB. So think about this way. So when you actually reach it at this point, this is very important. So when you reach at this point, I have this amount solid, this amount of liquid here. So that's actually the figure I actually draw here. And then solid is just stay as a solid. It's not changing. And then the liquid here, this is the liquid composition, this is solid composition. This liquid become this solid and this solid. And the previous solid is just as solid as it is. It's not changing. Okay? So we have actually two kinds of A phase. So A, which was existing before eutectic reaction, and A, which is forming from the liquid phase during the eutectic reaction. Do you understand? So just above, so when you have the invariant reaction, it's a little bit complex to actually draw the microstructure. So just above this eutectic reaction, you have this kind of thing. A was 75%. Oh, so this was 75%, and this was 25% here. Okay? And then this is now changing in this way. So this was A, which corresponds to 75%. And because this was happening just before the eutectic reaction, we call it pre-eutectic phase. Okay? Pre-eutectic phase. Okay? So we say this one, just more actually the scientific actual terminology, pro-eutectic phase. So just before the actual eutectic reaction. Okay? Pre-eutectic phase A is 75%, and then liquid was 25%. Okay? And then A is already solid. A doesn't want to make AB phase from the A, yeah? A cannot make AB phase. So A should be stay as A as it is. And liquid, 25% of liquid, which was at this composition, now start to cool it down, and then make this solid A and AB phase. Do you understand? So overall actually the ratio of the AB is, this is A amount, this is AB amount. That's overall level rule. But if you want to really have a little bit more accurate microstructure, we have original A, which is forming here about this amount, and then the remaining liquid is this amount. That remaining liquid have this composition, and that start to decompose to the A and the AB2. So there's the different A is forming. So A formed before eutectic reaction, A formed during the eutectic reaction have different actually the morphology. Okay? So A formed before the eutectic reaction is typically spherical shape or very nice facet shape. Okay, more like real, shape of the A itself, because there's isosomal actually, all this actually area, there's no actually the intervene by the solid phase. So A want to actually make its own crystalline phase without any intervene by the solid phase from the liquid. So A is forming, and then this liquid phase start to form A and the AB phase, AB2 phase. So typically when you have a eutectic reaction happening, I think you probably heard about lamella structure. It's a two-layer structure start forming. So A, AB2, A, AB2, this kind of layer because of the some limited diffusion process inside of actual liquid phase during the solidification. So if you start forming, it's like this. Let's do it in this way. This is better. So this is AB2, 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 AB2. And then in between, this color actually determines the two different phases. So you have mixture of this one, this black one is A, B2 phase, and then this blue is A phase. As I mentioned, this one is pro-eutectic. Pro-eutectic A, and both of this one, we call it eutectic A or eutectic AB. Because it's forming by the eutectic reaction. Okay, so the morphology is different. Okay, and this one was, in total, this one was 75%. Okay, these two together should be 25% because it's coming from the liquid phase. And the ratio of these two could be now calculated from this one. So because that liquid, that actually the eutectic A or eutectic AB2 is formed from this remaining liquid phase during the eutectic reaction. So this liquid, so this is the 0.4 composition basically. So starting composition is like 0.4, okay? And then you start to have AB and then AB2, A and the AB2, yeah? So the amount of the A is this minus this one divided by entire length, yeah? So the amount of A, so it's very complex here. So the amount of A is originally 0.25%, 25%. And then inside of this 25%, you have fraction from the Levy rule. So this one, 0.666 minus 0.4. So it's 0.266 divided by 0.666. That's the amount of the A. Is okay? From the Levy rule. And this one is originally 25% of the liquid phase. And then it starts from the liquid phase. So it's 25%. But the fraction of this one is now 0.4 divided by 0.666. Okay, so 2 together is still 25%. One more additional thing, you have to be very careful because this is not one molar element amount here. So this is 3 moles, yeah? 3 moles of element. So theoretically, you have to divide this one by 3 to get the mole of AB2, yeah? Is it okay? Do you get it? Because AB2, 1 mole of AB2. So when you say the amount, typically Lever rule is applied for the weight. It's not for the mole originally. But when you apply into the mole, you have to make sure that your system have only 1 mole of element base all the time. So even though we say that AB2, theoretically this AB2 in this diagram is A 0.333, B 0.666. Okay? So this is A 0.333, B 0.666 amount. Okay? That's phase amount. But if you want to say that, okay, how many moles of AB2 is existing, you have to divide this one by 3 again, yeah? This was one of the things I was stressed out in the probably previous actual lecture. So you have to be very careful because otherwise mass balance is not working. Is it okay? So this is the best microstructure I can expect from your answer, considering the eutectic reaction, really. Is it okay? More or less? I don't understand. Okay, everyone say I understand, but let me try one more thing then. Let's try one more. At this one now. At this composition. Let's start from 0.5. 0.5. Okay, we do exactly the same thing again, okay? At 0.5. Not going up. At 0.5, we do exactly the same thing. So now, I have liquid phase to certain temperature, and then AB2, and then eutectic, and then cooling down again. So this point here is about this point, yeah? So it's almost about 900 degrees Celsius. Let's take about 900 degrees Celsius. And this one, eutectic reaction, of course, 700 degrees Celsius, yeah? And then, so this is liquid plus AB2. Is it okay? Let's take again 3 microstructure. So at 1000 degrees Celsius, this is liquid anyway, and the liquid composition is 0.5 XA, 0.5 XB, 100%. In terms of mole fraction, 100%. Mole, not percent, it's atomic percent. Okay? Mole percent, yeah, mole percent, 100%, yeah. And then about 800 degrees Celsius. So 800 degrees Celsius. Okay? So let's take this point here as 0.45. So this is 0.45 and this is 0.66. Okay? So now so I will start to have this is AB2 phase, liquid phase, and liquid phase composition is 0.45, so 0.55 is okay? And then AB2, the composition XA, okay? The phase amount, so liquid, the amount of liquid phase. So liberal, so this divided by entire length. Yeah, the other side, yeah. Liquid is here, so liquid amount is this distance. So this distance divided by entire length, yeah? You good? So 0.66 minus 0.5. So 0.1666 divided by 0.45 to the 666. So 0.66 minus 0.45. How much is it? 216. That's amount of liquid phase. Amount of solid here, AB2 is 0. Now, then 0.5, so 0.15 over 0.216 times 100%, and then divided by 1/3 because of AB2. So, more percent of AB2 is divided by 1/3. Or times 1/3, sorry, not divided by 1/3. Divided by 3. Yeah. 0.05? Yeah, okay. 0.5 minus 0.45. You good? So, do you understand this one? No problem? You have to know this one. You have to understand what's the meaning of this. Okay, now, if I cool it down here. So, as I mentioned, during this eutectic reaction, if you look at it in that diagram again, so this is 700 degrees Celsius, and we are talking about this composition. So, just above eutectic temperature, I have this liquid phase and this solid phase, yeah? So, AB2, the microstructure AB2 is originally, you have this amount of liquid phase, this amount of the AB2 phase. So the original AB2 phase, the amount is so this is AB2 and this is liquid phase. And the composition, so this composition is now 0.6 XA, 0.4 XB, and the composition of this one is 0.66 XB and 0.33 XA. And the amount of each phase, the amount of this one is now this divided by entire length. So it's 0.15 divided by 0. So it's, this is 0.66, 0.266. And okay, this is amount at just above the eutectic temperature. So T equal to just above the 700 degrees Celsius, yeah? So just before the eutectic reaction. So we have this microstructure, and the amount of liquid phase is this divided by this one, so 0. Okay, so this is amount of liquid phase. You good? And then if you cool it down to now 500 degrees Celsius, so all the solid A was existing as it is, AB was as it is, okay, so this was eutectic AB2 phase as it is, and then the liquid which was in between this eutectic AB2 phase, it start to cool it down by itself and it start to making the solid phase. So the liquid was this one and it cooled down, it formed this solid and this solid phase. That actually should be here. So it will form A and AB2. Yeah. So A and AB2. So we'll have if you are using real chalk, it's much better picture, but it's not very good. So here, I have A phase, AB2 phase. Okay, the amount of each phase is, and the composition is very easy. The amount of each phase is, so this was liquid amount. Okay, so we have to take from that liquid amount, and then we have to take part of that as A phase, take part of that as AB2 phase, yeah? So the liquid amount was 0.1666 divided by 0.2666 times 100 times, now the fraction of A phase here, so from this liquid A and AB, so A is this amount divided by entire length. So 0.4, so 0.2666 divided by 0.666. That's the amount of A phase to send. Because we already multiply 100 for the percent here. So this is amount of A phase. Okay? Amount of AB2 phase. So this divided by entire length. So times, again, 1/3. Okay, why 1/3? Again, it's AB2 phase, yeah? Yep. Yep. 여기서? 네. 두 개 합치면 100%가 안 나오죠. 이건 퍼센트 단위가 아니라 사실은 사실 이제 정확하게 이야기하면 사실은, 정확하게 이야기하면 이건 퍼센트는 이제 웨이트를 이야기하는 건데 이 경우에는 몰이죠, 몰 양이라고 해야 되는 거죠. 몰 양이, 그러니까 원래는 사실은 1몰을 기준으로 했으면 사실 이 100이라는 걸 다 없애야 되는 거죠. 넘버 오브 몰, 리퀴드의 넘버 오브 몰, 그 다음에 AB2의 넘버 오브 몰. Sorry, I probably have to correct everything. I'm sorry. Yeah, you are very correct. So we should not say that 100% like this. So forget about all this 100%. So if we assume sorry. That's a very good point. If you assume everything as 1 mole of starting material, so I have 0.5 moles of A, 0.5 moles of the B, then how many moles of A liquid phase and how many moles of AB2 phase is forming? Or how many moles of A or how many moles of AB2 phase is forming? That's the final answer. Okay?
3분의 1 하기 전에 구하신 거는 A 0.333하고 B 0.666 페이지의 볼수죠.
So this one?
Yes.
Yeah, this is for 1 molar, yeah, 1 molar actually the phase. So A 0.66, B 0.333, yeah. B 0.66, A 0.333. For molar base, the molar elemental base. Okay? So it's a big complex because of you have molar actually phase diagram with some stoichiometric compound is more than the sum of actually the stoichiometry is more than 1. So you have to make sure that actually you are not overestimating the amount of the moles of each phase. Same thing for the previous one. I mean, previous one, even you have to actually take out all this 100%. It's not actually, it's not mole percent of the entire phase. I'm sorry about that. Do you get it? I'm expecting this kind of answer from you. If I ask you, okay, draw the cooling curve and then draw the schematic diagram, schematic microstructure of the system at the given temperature, you have to draw it in this way. And then you have to even say that what phase is forming, how much is the phase is forming from the dribble simultaneously. Is it okay? Any question?